Hi, so in this video, I want to go over kind of why we focus on just solutions and gases when considering equilibria, and then also seeing, how the gases can kind of be represented in their own way in terms of how we show the ratio of products and reactants in an equilibrated system. But so to begin, right, I want to just kind of elaborate a little bit more on why we ignore things like solids and liquids when we show our equilibrium constants or our mass action expressions. And so the reason for this is because, right, when we show that K constant, right, this is the ratio not technically of the concentrations of our products over reactants, but instead of the activities of those products or reactants. Now, activity is defined here as basically the concentration of a substance relative to its standard state. You may recall standard state from Chem 161, which was first mentioned when talking about like enthalpies of reaction and standard enthalpies of reaction, right? The standard state is kind of these guidelines that we as scientists have decided on to kind of just standardize things, right? Keep things pretty normal amongst, different conditions and stuff. And so within that standard state definition is kind of the following amounts for things that are aqueous, so like 1 molar for aqueous solutions, and 1 atmosphere for gases. That's referring to like, their partial pressures as they appear in different reactions. And so that standard state is again just kind of defined to keep things consistent so that when we do, perform the same reaction or the same experiment, we have kind of guidelines set out so that we're all doing it the same way. For pure like solids or liquids though, they themselves are already technically like in their standard state. And so we define their activity as just one. Now, when we take one and we multiply that by, all of the other stuff in our equilibrium constant, that obviously like won't change the constant itself. And so that's why we basically just ignore solids and liquids when writing out our equilibrium constant expression or calculating, say, like our reaction quotients or anything like that. But so, right, that's just kind of the background here. Now what I want us to take a look at is how gases are often represented, not necessarily in terms of concentration, but rather in terms of pressure. Now you guys should recall from Chem 161, the ideal gas law. So I want you to think to yourself kind of how molarity concentration is kind of within that law and how it relates to pressure. So I would recommend like pausing right here and kind of, thinking to yourself like, what is the ideal gas law? Just reviewing that. And then how does pressure compare to something like the molarity concentration? The molarity concentration is not necessarily written as like capital M for molarity in that equation, but it is kind of hidden in the ideal gas law as well. So hopefully you've done a little thinking on this and you've kind of figured out how the ideal gas law relates pressure and molar concentration. I have written out right here the ideal gas law as PV equals nRT. Now again, molarity itself is not technically like explicitly laid out in this equation, but molarity is just the moles per volume, right? So we can think of that as N over V. And so through this kind of rearrangement, I can show how pressure divided by the ideal gas constant and the temperature, that's equal to the molarity concentration. As a reminder, this is the ideal gas constant in units of liter atmosphere per mole Kelvin. We just saw our very recently used in a different context. I refer to that as the ideal gas constant for energies when we see like the joules per mole Kelvin version. This is the ideal gas constant for gases, right? So it includes units of pressure, it includes units of volume, right? So this is the R that we consider when using the ideal gas law usually and derivations of the ideal gas law. But so this kind of rearrangement shows that relationship between pressure and molarity. Basically, if you have a constant temperature, you can see how as pressure increases, molarity increases, right? They are directly proportional to one another. And so what that means then is that we can think of pressure in a lot of the same kind of contexts as we do molarity. So for instance, rather than just the equilibrium constant shown in terms of concentration, we can actually show that equilibrium constant in terms of pressures as well. Now to kind of distinguish the two, we're now going to refer to them as Kc for the equilibrium constant of concentrations, and then Kp as the equilibrium constant for pressures. But the way that those constants appear is essentially the same, right? There's still the products over reactants held to whatever power their molar coefficients are. It's just when we're using Kp, right, we use the partial pressures of our different reactants and products rather than the concentration. So kind of breaking down here like how the two K constants actually relate to each other. So I'm just going to like derive for you guys the relationship between Kp and Kc, starting with our expression for Kc, right, as the concentrations of products over the concentrations of reactants, and then subbing in for each of those concentrations that pressure divided by RT for each one of those chemical species. So right here I have like this big, huge fraction with like fractions within it. You're showing the pressure over RT for each of the products and reactants, again, held to whatever molar coefficient as the exponent there. Now this is a little bit messy, but we can actually kind of like simplify this because each of these partial pressures are being divided by the same R and the same T. So I can kind of pull that RT portion out of the equation, and then that's just going to leave me with the pressures of the products divided by the pressures of the reactants, basically the Kp expression. And so what that means overall is that the equilibrium constant of pressures is going to be equal to the equilibrium constant of concentrations times the ideal gas constant in the temperature. That portion of RT is held to some power. Now this power we define here as delta N. Delta N refers to the difference in the molar coefficients between our products and our reactants. So whatever the sum is of our molar coefficients, say for C and D, right? So we take the product coefficients minus the reactant coefficients. That's the delta N that we see here in this equation. Right, this equation is very helpful for just converting between, say, equilibrium constants of pressures and equilibrium constants of concentration, right? Just seeing kind of how that changes dependent essentially on, how much our molar coefficients vary. But so let's go ahead and look at some examples kind of using this equation and calculating the equilibrium constant of pressures. So consider here this reaction of nitrogen dioxide converting into dinitrogen tetroxide. Now let's say that at 100 degrees Celsius, the equilibrium constant for this reaction in terms of concentrations, so Kc, is equal to 4.7. What does that mean about Kp then for this reaction? Go ahead and pause, take a moment to try and calculate this out yourself, and then we'll go over the solution in just a moment. Okay, so taking some time here to calculate out Kp from Kc, we can again use that equation from the previous slide and the temperature provided right here. And what we should find is that we have a value of 0.15 as our Kp constant. Now, similar to Kc, Kp itself is going to be a unitless value, and so just 0.15, no units there, and we can kind of walk through, how I got to this answer. So we begin first with, again, that relationship of Kp equal to Kc times RT to the delta N power. Just kind of placing in the different values that I know here. I have 4.7 as my Kc. I have, again, the R constant is given to us as 0.0820576. Again, use the one that's in liter atmosphere per mole Kelvin. Then for the temperature, we of course want the absolute temperature, so I converted 100 degrees Celsius into 373.15 Kelvin. This is going to be, again, the products minus the reactants in terms of molar coefficients. So N2O4 has a molar coefficient of 1, NO2 has a molar coefficient of 2, so we'll say 1 minus 2 as delta N, again, the products minus reactants for that delta N value. And so I'm just kind of evaluating this out, right? I'll start putting together my different pieces of this equation, running through the algebra, and what I should get overall here is an answer of 0.15 as the Kp. So again, the equilibrium constant of pressures in this scenario is 0.15. Now, I use this as an example because it is kind of important to note that our usual understanding of the ratio of products and reactants relative to K is a little bit mixed up when it comes to the equilibrium constant of pressures. It's not entirely, it's just when we're on kind of the verge of, are products more favored or are reactants more favored? With Kc, it's very simple. If you have a Kc that's greater than 1, then the products are more common. Or if you have a Kc that's less than 1, then the reactants are more common. With Kp, because there's this RT factor kind of thrown in there, it gets a little bit more hard to read necessarily on whether products or reactants are totally favored in that. In this case, we see Kp be less than 1, but for Kc, it was greater than 1. So which are our preferred side of the reaction? Which side of the reaction is favored here? I would go based off of more of the Kc value to describe that. But if we did have like a much larger Kc, something that is like really obviously favoring the product, then Kp will also be like relatively large comparatively. So it's not like always going to turn out in this weird way where we're kind of like on the cusp of K being small or K being large. It's just specifically like in these cases where things are a little bit more on the fence, or you may see kind of this disagreement, we could say, between large and small. But so let's also look at another example right here. Consider this equilibrium of hydrogen iodide decomposing into hydrogen and iodine. This has a Kc of 54.3 at 25 degrees Celsius. So then my question here is, again, what is the Kp for this reaction? So you can go ahead and take another minute to pause, solve this, and then we'll go over the solution in just a bit. So this reaction is a little bit curious because if we go through and we run through that entire calculation of solving Kp from Kc, we should get 54.3 out from that. So the exact same value here. We can, look at the solution right here and see exactly why that is. So again, I have here my formula relating Kp and Kc. Again, I'll like plug everything into that formula. I've got my Kc value, my R, T, and then the delta N. Now here's the important point here is that when we look at delta N, we have, say, 2 moles of our products, right? One from H2 and one from I2. We also have 2 moles in the reactants. And so delta N itself is just going to be 0. So no matter what R and T are, when we put that to the 0 power, that's just going to equal 1. And so whatever our Kc is, it's going to be exactly the same as the Kp, right? Whenever we have matching molar coefficients on each side of the reaction, that is again the summed coefficients, and summed only taking the gas components of that reaction. So if any of these were solid or liquid, we would ignore them. But right, for all of the gas molar coefficients in this reaction, we've got the same number on the product side as we do on the reactant side. And so Kc and Kp are in perfect agreement. They're going to be exactly the same. All right, one last example right here, looking again at equilibrium constants of pressures, maybe how we actually like use that equilibrium constant of pressure. So consider here this reaction of nitrogen monoxide and oxygen gas forming nitrogen dioxide. So let's say that I have a mixture of all of these gases and it's at equilibrium, and I read the partial pressures of each of my reactants and products, and I find these amounts. I find the partial pressure of nitrogen monoxide is 1.20 atmospheres, the partial pressure of oxygen is 0.400 atmospheres, and the partial pressure of nitrogen dioxide is 3.15 atmospheres. So with these partial pressures, we can determine the Kp of this reaction. The way that we do that is again very similar to what we've done in our Kc examples. We simply take like the products over the reactants, and we just solve for whatever our K constant may be from these equilibrium partial pressures. So go ahead and take a moment to work on this, and then we'll discuss it in just a minute. All right, so working through this one, right, using these equilibrium constants of pressures, I got for my Kp for this reaction 17.2. So again, kind of how I will think through this is by taking the partial pressure of NO2 squared, because it has a molar coefficient of 2. I divide that by the partial pressure of NO squared and the partial pressure of O2. Again, it follows the same kind of general formula as we've seen in Kc and in Q. It's products over reactants to whatever power their molar coefficient is. And so just placing in these different partial pressure amounts, I can then solve for Kp itself, and I get 17.2. Now, as a follow-up question, what if I wanted to find the Kc for this reaction? Go ahead and solve for Kc here, right? Think about how you may be able to solve our equilibrium constant of concentrations instead. Okay, now working through this one, right, I'm going to use that same equation that we saw before, but this time I'm going to set it up to solve for Kc. So, right, what I get from that is 421 as my Kc value. Let's take a look at the math here, right? Same equation that we saw relating Kp and Kc, but now, right, it's kind of going to be a little bit flipped, right? Because before I was solving for Kp, this time I'm going to need to solve for Kc itself. So I'm just going to, algebraically place everything that I know into this equation and then kind of solve for my one unknown here. Again, kind of setting this up just in my math, you can see I have the delta N as -1 now because we have 2 in the products and 3 total in the reactants. And then again, right, keep in mind that we need to convert that temperature into the absolute temperature. This is often something that people kind of forget about when using this equation. But so solving for that, right, and kind of work through the algebra right here, and I find Kc equal to about 421. With this equation, we can go from Kc to Kp, or we can go in the reverse direction, right, Kp to Kc. Either way works. It's just a matter of like keeping track of which one we're actually solving for, keeping track of all of our different pieces of this equation. But so, right, that kind of introduces us then to, again, the gas side of equilibrium. Equilibrium is generally only relevant to like aqueous or gas phase products and reactants, but sometimes, right, when we do have like all gases, it's very common to see then this equilibrium constant of pressures being used to express that perfect ratio of products over reactants. But so please let me know if you have any questions, and I'm always happy to help.